Hello and welcome. This is the pre-lecture video for Chapter 12. This will be our only pre-lecture video for this particular chapter. And this is also our very last pre-lecture video of the semester. So I appreciate all of the clicks I've gotten on these videos. I hope you've gained a lot of information and been able to use these videos in a productive way for your studying. Look for a survey to appear in about the next week or so about these pre-lecture videos so I can learn a little bit more about what I might do in the future to help improve these types of videos. Good luck to you on the final, and good luck to those of you continuing along in chemistry. Okay, so Chapter 12, our limited objectives that we'll be discussing here are just trying to describe the difference between crystalline versus amorphous solids, try to talk about unit cells and what that means, calculate empirical formula from looking at a unit cell, so we have to get an idea of what a unit cell is and see how that relates to some properties of a given substance. We want to relate the unit cell to density. We're going to do this qualitatively. You can actually do this quantitatively, and it is quite gory and pretty boring, but we're only going to take a look at this in a qualitative sense. We're going to look at a model called the electron C model, or C of electrons model, to describe metallic bonding. We'll also briefly discuss a little bit about a breakdown in this model, and maybe take a quick glance at what a molecular orbital picture might look like for metals, and then be able to predict empirical formula from the unit cell / structure of an ionic solid. And maybe lastly, there's not one listed here, but just get an appreciation for the different types of solids that we might encounter. For example, some solids could be metals, some could be ionic solids. We know water is a molecular compound. Maybe a different type of solid's a polymer. So we like to just get a sense of what these different words mean. And I think for the most part, we probably have a pretty good appreciation for the different types of solids, but we just want to make sure we have a molecular view of all the various types of common solids. Okay, so we can classify solids based on bonds. So metallic solids are held together by a C of collective shared electrons. We were talking about this a little bit in class on Tuesday on how you have all these nuclei on your metal atoms. The nuclei are highly charged, so you have these highly charged nuclei, lots of electrons that just flow all throughout the metal surface. So it's kind of hard to look at a metal and figure out which electrons belong to which particular atom. Whereas you can do that pretty easily within an ionic solid. You have all these minus, pluses. You know kind of exactly where your electrons are at any given moment within an ionic solid. Pretty similar within molecular solids. So let's say you have something like HBr. So let's say you have an H, or that's probably the bromine. So if you have a bromine and an H, you have a bond between the two. There's two electrons between those two atoms at any given moment, and there's just intermolecular forces between the molecules. Finally, covalent network solids are the case where you have covalent bonds linking all the atoms in your structure. So you have two electrons at least between two of the atoms if they're all single bonds. So ionic solids are cations and anions that are mutually attracted together by electrostatic forces. Covalent network solids are the description of a three-dimensional array of covalent bonds. This is the type of bonding that you see in things like carbon solid, so like graphite, diamond. This is the type of bonding you also see in things like silicon. Molecular solids then are described by molecules, where the individual molecules are being held together in the solid by the weak or relatively weaker intermolecular forces. Regardless of the type of solid that you have, whether you're talking ionic, metallic, even when you look at water and some other types of molecular solids, as well as the covalent networks, you can describe the solid as either being crystalline in its nature or amorphous. And a crystalline structure is one that generally would appear brighter, be a bit more brilliant. So diamond, of course, would be a crystalline solid, just from the thought of it being a brilliant, bright solid. And the reason why is if you have light particles coming in on this and you have a very regular pattern, then light's being reflected off of these solids in a very regular way. If you have light come into something like an amorphous solid where you don't have a regular pattern. So an amorphous solid is described as having the atoms arranged in kind of a random pattern. So this is going to lead light to scattering off in different directions. It will lead to some of the light being shifted in different types of wavelengths, so you'll have a more dull appearance instead of a bright, brilliant appearance. So you get a brighter, more brilliant appearance when solids have their atoms arranged in a very regular pattern, fitting what we call a crystalline solid. Then you'll have more of a dull appearance whenever you have an amorphous solid, where you lack that arrangement of the atoms. So crystalline solids have a regular pattern, and well, it says they are of more interest to chemists. That's kind of a weird statement. I mean, they are of more interest to maybe chemists who like to study X-ray crystal structures. If you don't have a crystal, it's kind of hard to study a crystal structure. So you can maybe study more interesting properties of crystalline materials through some chemistry means. But we'll take mostly a look at the crystalline solids here, because we can take a look at that regular repeating pattern, try to figure out what it is, and describe that pattern with what we often call the unit cell. So the unit cell is the simplest repeating pattern of the solid. Now, you don't get a unit cell with an amorphous solid. You would only get a unit cell with a crystalline solid. So you wouldn't have a simple repeating pattern for the amorphous type solid. So the structure of a crystalline solid is defined by the size and the shape of the unit cell and how the atoms are arranged. And so the geometric pattern of the cell is what we call the crystal lattice. And so if we look at metals, so metallic structures often take one of three different types of unit cells. A primitive cell is one where the metal atoms are just head-on-head. So if you have metal atoms just simply attached in a head-on-head arrangement in 3 dimensions. So you have to picture this going on in all 3 dimensions of the solid. And so this will be going on in, like I said, all 3 dimensions. So this is just a simple head-on-head arrangement is our primitive cubic. So a PC or a primitive cubic is this type of solid. A body-centered cubic is a cell where we have one in the very middle of the cell, and then we have 8 atoms on the corners of a cell. So you have 1 atom in the middle, and you have atoms above and below. And so the difference here is you have a little bit of a better packing efficiency with your body-centered cubic. Primitive cubic is really wasting a lot of space. I think this is on a different slide a little bit later, but we'll say right here that 52% of space is occupied within a primitive cubic. It's 68% within the body-centered cubic, and a face-centered cubic is slightly better. This is where we have an atom on the face of a cell. Kind of hard to see here. Let me zoom in a little bit. So we have an atom on a face of the cell, and then we have atoms on each of the corners. So each of the faces has an atom, and each of the corners has an atom. The repeating pattern is would mean that you have the exact same unit cell right next to the unit cell. So here you continue having an atom on the face, atoms on the corners. So the unit cell is just trying to tell you that simple repeating pattern of your cell. We'll get into a little bit of trying to count atoms within these unit cells and how only 1/8 of an atom on a corner is within a particular unit cell. The atom in the center of the cell is completely within the unit cell. So like a primitive cubic really is only showing us 1 atom. Because we only have 1/8 of each atom, 8 atoms, only gives us 1 overall atom within 1 unit cell. A body-centered cubic has 2 atoms, because we have atoms on the corners and 1 in the center of the unit cell. And then the face-centered cubic, we still have atoms on the corners, so we have that atom, and then we have 6 faces with half an atom on each face, because half the atom on one face is in 1 unit cell, and the other half the atom would be in the adjacent unit cell. That would be in the 3 dimensions sticking away from the particular unit cell. So that would have 4 atoms. So we're using space a little bit more efficiently within a face-centered cubic, getting 4 atoms within 1 unit cell. That's 74% of space being utilized. So we're utilizing space better within the face-centered cubic, a little bit less efficiently within the body-centered cubic, and worst within the primitive. Now you may wonder, why would anything adopt a primitive cubic and waste space? Well, the issue is complicated. Very few metals actually adopt a primitive cubic structure, and most likely it's going to be just a consequence of the quantum mechanical nature and the way that the given orbitals on a particular metal might overlap best. So maybe you get better overlap with a slightly poor utilization of space. So the cubic structures, this is a little bit of a different type of picture where we can see the primitive cubic, you're getting 1/8 of each atom within 1 unit cell for the corner position. So an 8 times 1/8 gives 1 atom. Here we have that same 1 atom from the corners plus the 1 in the middle for 2, and then the 1/8 of the atoms at the 8 corners plus the half on the 6 faces. So you have to look at a unit cell and figure out how many atoms within the unit cell are actually within 1 single unit cell. So if you have an atom on a corner, it's being shared within 7 other unit cells. You'd have the cell to the one side, above on top on the other corner, and front on the side. So you have to picture all these unit cells, other unit cells would be sharing an atom given the particular position of the atom on the unit cell. So close packing deals with the idea that nature, generally doesn't like to waste space. So atoms can try to adopt a structure where they're as close together as they can be. There's two types of close packing structure. One's called cubic close packing. The other one's called hexagonal close packing. And they are slightly different in terms of their unit cell, but they both utilize space exactly the same. So they're both utilizing space at 74% utilization. Now, metallic bonding, we mentioned earlier, the sea of electron model. We have all the nuclei that are highly charged, all these valence electrons that more or less flow through the metal. This type of model can explain why metals are malleable and ductile. So you can pound metals, the nuclei can just pound, and then the electrons just flow with them and take whatever spots are on the nuclei, almost as if, you're just pounding this into a sheet, and the electrons readopt a new position surrounding all of those nuclei just the same. You can stretch this into a wire. So metals are malleable and ductile, and the sea of electron model helps us understand that. And you could also explain the conductivity of metals. So if you were to take an electron away from your metal and remove an electron, all the other electrons could flow towards that missing electron. So you can explain the electrical conductivity with the sea of electron model. One property that you can't quite explain is the melting point trend of the transition metals. If you look from left to right, melting point increases, but only about halfway across the transition metal series. So our melting point increases from potassium to calcium, and it continues across the scandium-titanium series. And about halfway across the transition metal series, then the metals start to drop in their melting point. Now, it's probably not so surprising that this happens, because we saw that metals generally are decreasing in melting point as they grow larger, and mercury was the one that ended up being a liquid. And so zinc and cadmium actually weren't so far away from being liquids as well. I mean, they're relatively high in terms of their melting point, but mercury ends up having a melting point below room temperature. You get this dropping in melting point not because of the electron C model. Electron C model would probably say you have more highly charged nuclei, even more valence electrons, and even more electrons to distribute around those nuclei. That the sea of electron model would probably suggest that the melting point should have just increased from left to right through this series. If we start thinking about the idea of the overlapping of the metal orbitals, now I don't want to get too complicated here, mainly because I'm not even all that fluent on what these types of overlaps look like. But if you start picturing having your D shell with, say, one electron, like you're the first transition metal element, you're getting a bonding contribution. So if you have two d electrons in your titanium, then you're getting two orbitals that are both a net bonding type orbital. So then you go like with 3 or to 4 electrons, and still you're coming up with putting your electrons into your bonding orbitals. So you can manage to fill, let's see here. So from thinking about this problem, like in chapter 5, we're going to get 5 bonding type orbitals. And then we'd have 5 anti-bonding orbitals. So maybe call these the D star, call these the D, the D bonding. Now, whether these are sigma or pi and whether or not they're degenerate or not, that's not something I know much about. But what I would know, or what I think makes a lot of sense, is we'd get 5 bonding set of orbitals and 5 anti-bonding set of orbitals. So as soon as we get to like manganese, we get like halfway across the transition metal series, we'd be filling in our 5 electrons, or other 5 electrons, and then we'd be completely filled in our d orbitals. And then if we start to go to then iron, and then the next larger transition metal, we're now putting electrons in the anti-bonding orbitals. So as soon as we start filling electrons in the anti-bonding orbitals, we're like destabilizing the metal. We're making a poorer metal structure, or a weaker structure perhaps, and then hence maybe one that would have a lower melting point. So as we start filling more electrons into our anti-bonding orbitals, we're moving to metal atoms that aren't as highly attracted to each other as they were when we were filling electrons into pure bonding orbitals. Okay, so maybe a molecular orbital picture would help us understand that once we get halfway across the transition metal series, we're filling electrons into anti-bonding orbitals. That's going to destabilize the structure and start lowering their melting points. So some rules here. on molecular orbital theory. Atomic orbitals combine to make molecular orbitals that extend across the entire molecule. A molecular orbital, just like from chapter 6, and likewise when we were discussing this in chapter 7, I believe, that molecular orbitals contain 0, 1, or 2 electrons, and never more than 2 electrons. The number of MOs equals the number of atomic orbitals. So when we look at our atomic orbitals, if we have 5 atomic orbitals on one atom, 5 on the other, we can make 5 molecular orbitals that are bonding and then 5 anti-bonding. So we make half of the orbitals bonding, half anti-bonding. And so as soon as we start adding electrons to anti-bonding MOs, we're going to weaken the bonding. So we're strengthening the bonding by adding electrons to bonding MOs, and then weakening it by adding them to anti-bonding molecular orbitals. So moving into ionic solids, they're held together by electrostatic attractions of the cations and anions. Of course, they have high melting points and boiling points, and these are certainly crystals that we know salt looks like a crystal and all that. And they behave as insulators in a sense that a salt is not conducting charge. It's really hard to rip an electron off an atom and have all the electrons flow towards it. So there's really no easy way of picturing ionic solids as behaving as conductors of electricity, and so they don't conduct electricity. Now, that just means that they're going to behave more as insulators than they are as conductors. So now the structures of ionic solids in terms of their crystal patterns, in the case of having 1-to-1 solids, so the 1-to-1 for the plus to minus for one cation to one anion, tend to fit one of 3 different types of crystal structures. Cesium chloride takes what we would call a primitive type lattice. This is when we're going to have, say, a chlorine here and then a cesium right in the middle of the box. So we'll have a cesium right in the middle of the box. So every time that there's an atom, there's another cesium sticking straight in the middle of the box. So the structure ends up looking like a body-centered cubic, but where we have 2 different types of atoms. We have our minus atoms on the corners, and then we have a plus in the middle. And one of the things you can characterize a particular unit cell by is perhaps the coordination number of the atoms relative to each other. And so I think we could see that the atom in the center is in contact with 8 atoms. So the coordination number of the cation in the center of the box would be 8. And the coordination number of the anions would have to be the same since it's a 1-to-1 salt. So if we were to think of all the neighboring unit cells, we'd have another red atom here. We'd have a red atom sticking straight up and out of the box. I mean, you'd have to picture this quite a bit, but the coordination number of both atoms would be 8. And that's primarily because it's a 1-to-1 crystal. And so if we look at the sodium chloride structure, we see it looks like a face-centered cubic. So it kind of looks like sort of 2 face-centered cubics where we have chlorides on the corners and we have the sodium atoms. So we have our minuses on the greens and then pluses on the purple atoms. So notice we always have plus minus, plus minus, plus minus. We don't have minus in direct contact with each other. They're sandwiched or have plus cations in between them. And so we could look here and try to figure out a coordination number. One of the things within this cell would be that the center of this box is going to have an atom. It's one that we can't see, but there's going to be a purple atom right in the center of the box. There's a purple atom right inside of the box. And so that purple atom is going to have a coordination number of 6 because it's going to have the atoms that are on the faces of this unit cell, the green atoms that are on the faces, and there are 6 faces in direct contact. So that purple atom in the center would have a coordination number of 6. We could also perhaps think of the green atom here. So take a look at this green atom here and see that it would be in contact with the 4 purples, and then the 1 purple in the center for 5, and then the 1 purple that would be in the adjacent cell sitting right in front of the unit cell that we're looking at. So we'd have a coordination number of 6 for both the plus and the minus ions within the NaCl structure. And so finally, the zinc blend structure is apparently, it's called, looks like we have a sulfur on the corner and then a zinc on the face of the cell. excuse me, a zinc sticking into the cell within sometimes what's called a tetrahedral spots. So it's sometimes hard to see, but you have these gray atoms that are in tetrahedral spots within the cell. So you kind of have the tetrahedron type arrangement within the cell of your zinc atoms, and then the sulfurs on the faces and the corners. Okay, so if we go to our counting techniques and counting atoms, that's another thing we might do here is look at that we have 1/8 of the atoms on the corners times 8. We have atoms on the faces. There's 6 faces, half on each face, so that's 4. Then we have 4 atoms completely within the unit cell in terms of the zinc. So we have our sulfides, 4 of them, and we have 4 zinc 2 plus ions. So now the coordination number is a little bit different here. If you think of each zinc, it has a contact with 4 atoms. So we have a coordination number of 4 for each of our atoms within the zinc blend structure. So what's changing here within the lattice is the coordination number of the cations and the anions. And the reason why we have 4 different types of unit cells for what are all just 1-to-1 plus cation or 1-to-1 cation anion type cells is we have a much differing relationship between the relative size of the ions relative to each other. And so in the case of sulfide's the biggest ion. Zinc is actually going to be pretty small here relative to the size of zinc. Sodium and chloride are a little bit closer together, but they're about equal sized in the case of cesium chloride. And so whenever your plus and minus cations are about equal in size, then your coordination number can be relatively high. The coordination number is going to be a little bit lower whenever your ion's getting bigger than the cation. If it's even bigger, then you drop even further in terms of the coordination number. And so this slide here is kind of showing us the relative size of our anion compared to our cation. So about equal in the case of cesium chloride, so we go with a high coordination number. If we have a perhaps intermediate size between our anion being big, so of course we remember anions are always bigger than their neutral counterparts, cations are smaller. So cations are usually on the smaller end. So our sodium is smaller to a little bit of a bigger extent than chloride is, and so here we drop to a coordination number of 6. And then the case where the anion grows even bigger, the cation size is even smaller, then we adopt an even lower coordination number. So we're just changing the coordination number, and as a result, the solid takes on a different form. Now, if zinc, you could go through and think about some kind of weird type questions, but if zinc sulfide were to take the cesium chloride structure, its density would be higher. So if it were somehow to adopt a different type of lattice, it would have a greater density, so it would be able to pack more mass into a given size or a given volume. But the issue would be that the anions, being so big, would get too close together. So the anions would start to get too close together and repel each other, which would be particularly bad. So there are some geometrical reasons why solids are adopting the types of structures that they do. And for what I'd like us to walk away with is just the ability to inspect a unit cell and try to get something like the empirical formula of the compound out, get a sense of where the atoms are. And so we'll take a look at a couple examples in class to try to get a sense of how we can take some information away from a cell, be able to work out things like coordination number for the atoms, and then maybe just mildly understand that there's some geometrical reasons why some different types of solids emerge. And so if we look at some different types of solids, NaF, this is actually the exact same structure as NaCl. So this is the NaCl structure, but for sodium fluoride. So sodium fluoride is adopting the same general type structure as sodium chloride, coordination numbers of 6 and 6. The magnesium fluoride, though, like we probably know that that's MgF2. So MgF2 should have twice as many anions as cations within the structure. And so if we look at the particular structure, we have atoms on the corners, and those are the magnesiums, and we have one in the center of the box. So that's 2 magnesiums overall. The fluorides are actually a little bit hard to see. We have 2 on the face here, 2 on the face here, and then we have this one and this one totally within the unit cell. And we can see that just by the virtue of these bonds being shown to us here. So this atom is completely within the cell, as is this atom here. So we're getting Let me put these atoms in green here. So these ones here, we only get a half within the unit cell. So that's 4 times a half, because those are on the face of the cell. So that gives us a total of 2 for the face ones, for the F minuses, and then we get 2 totally within the cell. So we get 2 atoms totally within the cell. Since they're totally within the cell, we count 2 times 1. So 2 plus 2 is 4. So we get 4 F minuses and 2 Mg pluses, hence the empirical formula MgF2. And so our coordination number would also show that the fluorides are going to have a coordination number that's half of the cation. So if you look at each of the, let me clean this structure up a little bit. Let me do some erasing here. So if we try to figure out a coordination number for our compound, so we would have, let's see here. So magnesium would be in contact with 1, 2, 3, 4, 5, all 6 of those anions in the box. So magnesium's coordination number is 6. And then if we take a look at one of the F minuses, so we have 1, 2 atoms it's in direct contact with, and then 3 for the one in the center of the box. So only coordination number of 3. So we have to have this relationship that the coordination number has to be the same ratio as the formula dictates. So the coordination number of the cation is going to be double that of the anion. And that's because the cation should be surrounded by twice as many of the anions as the anions are by the cations. So scandium F3, so SCF3, we have atoms of F on all of the edges. So we have an atom of F on an edge. So that atom is going to be shared by 3 other unit cells. So here we're going to have a quarter of each of those atoms, and there's 12 edges. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. So that gives us a total of 3. That's the F minuses. And then we have scandiums on the corners. And so that's an 1/8 times 8 corners for 1. So that's 1 scandium 3 plus, 3 F minuses. So we get the right ratio SCF3, so we get the right empirical formula out. And then if we start tracking the coordination numbers, we get shown here this extra bit to maybe help us out to see that the scandium blue atom is in contact with 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So we get a coordination number of 6. And then let's clean this up to try to get the other coordination number. Of course, we know it should be a third. But how can we see that the coordination number of each fluoride is just 2? Well, let's just look at an atom on a corner and see that this atom here on the corner is in direct contact with 1, 2 atoms. And then that would be it. And so there's no atom here, no atom here, no atom in the center. There's no other atom that F is in contact with, so just a coordination number of 2. So molecular solids. So molecular solids consist of atoms or molecules held together by the weaker forces like dispersion, dipole-dipole, hydrogen bonding forces. So like benzene, toluene, phenol. So what goes on here, we have benzene, probably can get a little bit closer together. It doesn't have this extra group kind of perturbing its structure, so it has a relatively higher melting point. Toluene is going to have a little bit of a harder time due to having a slightly more bulky nature to it. But switch that bulkiness to a hydrogen bonding group, then all of a sudden you strengthen the intermolecular forces. So toluene goes weaker, phenol goes stronger in terms of its intermolecular forces compared to benzene. Now, if we think of graphite, graphite's pretty interesting molecule in that it is a much different type of structure and a totally different set of properties than diamond, which is another allotrope of carbon. But one of the main things that's interesting with diamond versus graphite, diamond's a 3-dimensional array of covalent network bonds, but graphite is 2-dimensional arrays of covalent network solids. So graphite contains these graphene sheets where you have a 2-dimensional array of carbon atoms connected that then have dispersion forces that are linking together the next sheet. Now the sheets are pretty big, so the dispersion forces are pretty strong, so the melting point of graphite is still pretty high. So if you want to take the lead out of your pencil and melt it, it's going to have a very high melting point. I mean, I don't suggest you try to figure out what it is, But you can use a pencil because these sheets separate from each other relatively easily. So if you glide a pencil, these sheets are going to separate from each other pretty easily, so that you can just easily separate off the graphite sheets. So you leave the sheet intact, but then you can use the pencil to write with. So graphite's an interesting example of a molecule that has covalent network bonding within it, but then also intermolecular forces uniting those two-dimensional sheets of carbon atoms. So lastly, for today would be the covalent network solid. Diamond is a great example where we have a three-dimensional array of tetrahedral carbon atoms. So you just have all these tetrahedral carbons going in all three dimensions without the structure. So you get a complete three-dimensional array of covalent bonds linking the atoms together. These types of structures end up having a very high melting point and boiling point. Diamond's very hard, so it's a very rigid structure because these bonds are very hard to break. So it's very hard to rupture these bonds. If you compare this with like your plus minus with your like sodium chloride structure, you have all these plus minuses. You can kind of break these ionic solids together at any particular part, and then the solid's just fine. So I mean, you can imagine ionic solids being more brittle, and then the covalent network solids being much more rigid as a result of just the nature of the bonds being strong, harder to break. The ionic bonds, while stronger in nature, like the plus minus interactions are stronger, but you can break the solid at any of the particular points, and you'll just get some new plus minus interactions to replace the ones that you just broke. So you can sort of break an ionic solid at any particular point much more easily than you can the covalent network solid. So we'll talk, we haven't talked today about the polymers. We'll see a slide in class to introduce us to polymers, but that's basically a quick introduction to what we hope to gain from a chapter like chapter 12 for a little bit greater of an understanding of the different types of structures of solids, to gain a little bit of an insight into the molecular behavior or a molecular picture of solids. Thanks for the attention. See you in class.